Hello. How's it going, Christina? I'm doing good. Almost done with your quarantine. But there we go. Okay. So once you download that, you can see, let's go to assignments. We have an assignment on predicting these products. If you read that and look at the activity series, plus also the solubility rules, you should be able to, let's see, where are you? No, predicting, no, not that one. The products, that one. You should be able to do this one. Now it was due February 8th, and if you weren't able to do it, I can give you an extension since I know you didn't. Good, I'm glad you can download it. Excellent. Because that's one of those things I wasn't sure if that was the one or not. Okay, so the predicting the products, like I said, it was due the 8th, and I haven't checked to see who's turned it in because it's only been 2 days ago, but basically you just had to use those rules, right? And if no reaction would occur, you would write no reaction, and just based on what you know, you would predict these. Okay, let me see. Let me close that. Go back to the modules, because today we're going to start, well, we already started actually on stoichiometry, but mainly we did mole conversions, because mole conversions are, are like the beginning of stoichiometry. So where are you, mole conversions? Okay, yeah, right here. There. This area where it says mole conversions, there's a sheet that I used for practice, but we didn't do all of them because we know how to do them already. But I just wanted you to be able to know, to remember, right, how to do these. And this is one of them. Okay, so you had to calculate the number of atoms in 2 grams of platinum. The way that I do that is, let me see, let me insert a table. We use dimensional analysis, so let me make it a little bit bigger so you can read it. Okay, so what you know is 2 grams, right? 2.00 grams of platinum, so PT. Okay, so if you look at your periodic table, which I have to grab mine, hold on. Right, there it is. Okay, so if you look at your periodic table, you can see that platinum is normally, let's see, 207.8 grams per mole. 0.8, 0.2, 0.2. I don't know where I got the 0.8. No, see, I'm looking at the wrong one. I'm looking at the wrong, I'm looking at lead. I meant to look at platinum. Okay, 195.08. That's what it was. Okay, and that's grams in 1 mole of platinum, right? Of platinum in 1 mole. Okay, so basically this is it. You don't need the rest of it, but I always insert this much. So what you would do is you would multiply, oh wait, no, because it says number of atoms, sorry. I did not see this part. Okay, so that next, in 1 mole, you know Avogadro's number, right? Of platinum, there are 6.02 times 10 to the 23rd molecules or atoms, let's just say, because in this case it's atoms. We usually say particles, but that way it covers everybody. But this is very specific to atoms, so we'll do atoms. Okay, so that's what you would do, and then you would just multiply and or divide whatever needs to be divided, right? Or multiplied. Hold on, let me get my calculator. So it's back here and here. All right, here we go. All right, so when you multiply, you would multiply 2 times 6.02 and divide it by 195. Okay, so 2 times 6.02 and then divided by 195.08. And that gives you this number, and I'm going to put it down here, is 0.00. And we have 3 sig figs of 617. Now, that is how many times 10 to the 23rd, of course, right? All right, so as you know, when you're doing atoms, when you're doing sig figs, I mean, excuse me, you need to increase the number so that it's in the right spot. So that's, we're increasing it by 3, so we need to decrease this by 3. So that would be equal to, which kind of makes sense because that's a very small fraction of that. And 1 mole is what we're looking at. Okay. So it would give us 6.17 times 10 to the 20, right? Atoms of platinum. Okay. All right. And there you go. And that would be the right answer for this particular one. Okay, here we go. I got it. I have to grab all my stuff one at a time as I need it because it's all put up in my briefcase. So I slowly got to get one at a time. Use it for everybody. Okay. All right, let's see. Okay, mole conversions. That is chapter 11 in my book that I'm using, my practice book. All right. And these are mole conversions. Okay, where are you? Make this. Oh, there we go. Chapter 11. We're getting there. Okay. So 6.17 times 10 to the 21st. Oops. I moved it too many times? No. Wait, maybe there was another extra 0 that I missed. Yeah, I put 1 too many zeros. I was like, something's weird because it should be to the 21. Yeah, there we go. So yeah, just to you move it 2, you decrease it by 2. All right, atoms of platinum. All right, so there you go. That's how you do that one. And it's pretty, like I said, it's pretty self-explanatory. Looking at that, you needed the molar mass and then Avogadro's number. Same thing with this one and with all the others, except these are, let's do one that's going one way and one that's going the other way. So that way we get both. I will do this one next. I'm gonna insert same table. You probably don't need 4, but I like putting 4. All right, so we have the what we know first, right? Times 10 to the 23rd. and that is atoms of mercury. Okay. 10 to the 23rd. Okay. So they want to know how many grams. So we're doing the same thing, but reversed. So obviously atoms is going to go on the bottom. So we got 6.02 times 10 to the 23rd down below. And that is atoms of mercury in 1 mole of mercury, right? Okay. All right. And then now we need to know how much 1 mole of mercury weighs, right? And for that, you need your periodic table. And according to it, it says it's 200.59. So it's 200.59 grams of mercury per mole of mercury. All right, and there you go. So now all you would have to do is the reverse. You multiply the top divided by the bottom. And then you can take care of your exponents if you don't have that kind of calculator. But if you do, you know, you can do it all at once. And I'm just doing it without the calculator just in case. All right, without the, you know, the scientific calculator. Divided by 6.02. Okay, so that number that I get right here is 39. And we can only have 3 sig figs, so 39.7, right? And that would be times 10 to the what? Okay, so the top one is 23, the bottom is 23, so they would cancel out, right? So 10 to the 0, basically, grams. And that would be grams of mercury. So you have 0, sorry. I meant to bring this down, grams of mercury. All right, so obviously this is weird to looking at it like that. So you can just say 39.7 grams, right? And that would be good enough. Or if they wanted it in scientific notation, it would be 3.97 times 10 to the 1. But we can just give the 39.7 grams of mercury. And there you go. So you can go backwards or forwards, but you notice that one of them is dividing. You kind of flip, but you notice that when you flip, you don't flip the numbers also. You just flip the whole thing. They come together. So atoms are always with 6.02 and 1 is always with mole, right? In this case. All right. Okay, so we're going to move out of here. And then this is using molar mass of a compound. So far we haven't used molar mass of any compound. So I'm going to go ahead and do the top one. And for that one, we're going to first have to calculate the molar mass. So the molar mass says that is 6 times 12.01 because we have that many carbons, right? And then we're going to have 6 times 1.01, which is how many oxygens we have. I mean, not oxygen, sorry, hydrogens we have. And that gives us a total of plus 6.06, okay, that is 78.12. And that is our molar mass of benzene. So that's grams per mole, oops, per mole, and my period did not come on. Must have hit something weird. Okay. And this is of C6H2, H6, right? 6H6. There you go. Which is like this, but or you can call it benzene, whatever you want. Oops, if you want to do it the better. Stop that. Okay. All right. So that is it. Now that's the molar mass. Now, how do we calculate the rest? Well, we've been doing it all along. So what we need to do is we insert the table like I do because let's do a 4 anyway. even though we probably will not need but one. All right. So what they're asking us is 17.2 grams, right, of benzene. I'm just going to copy this, be easier. There we go. All right, and we say that for 1 mole of benzene, right, we just calculated it, 78.12 grams of benzene. All right, so all we would have to do is multiply, divide. Well, obviously multiplication is times 1, so we're just dividing. 17.2. Oops, see, I told you sometimes my keystrokes are too light. Divided by 78.12. That gives me 0.220. And since we got to have 3 sig figs, the answer is 0.220. And that would be moles of benzene. Okay. Look at sig figs in here too, every time. Sig figs are important in our chemistry, you know, in this discipline. All right, now this one is the opposite. It says determine the mass. Okay, we still got to figure out the tin 2 sulfate mass. So we need to do that first. We do that molar mass. And for that, we got tin, which is, where are you, tin? It is 117.71. 18, sorry, did I say 17? 118.71, sorry, grams, right? And then we are, oh, there's only one of those, so we don't even need the parentheses there. Then we add, and they're all grams, so we're just going to skip the gram part. Plus, we've got, based on the formula, we got 1 sulfur at 32.07, right? And then we also have 4. This time we do need a parentheses, times 16 for the oxygen. All right, so now we do the molar mass. That gives me 214.78 grams of tin 2 sulfate. So I'm just gonna, maybe I can just copy this one. Hopefully it'll let me. And now I don't have to rewrite it all over the place. Yay, there we go. Per mole, right? Oops. I hate when that happens. Per mole. Okay, there you go. All right, so that's grams of that per mole. Yeah, all right. So now we need to do the same thing. We insert our little table with the 4, right? And we start with what we know, which is 0.187 moles of this, right? And for that, we have, see, moles goes on the bottom this time because moles is on the top here. Is equal to 214.78 grams. Okay, so here we're multiplying 214 times 7.78 times 0.187. That gives us 40.2 because it's 1/6. So 40.2 is our answer right here. Sorry. I don't know, sometimes 40.2. And that is grams of this stuff, right? And that would be the right answer for that one also. All right. You can do the rest if you really want to, but I mean, we just wanted to review real quick how to do this, because we're now going to do what is known as a limiting reagent. And, you know, all of this is just there, but like I said, we don't really need these. They're just a quick review. So don't save. Let's go to the next part. Right, so go back to the module and look at what mole, let's see, stoichiometry. Let's look at, where is my stoichiometry? I think this is a PowerPoint. I want to say it is, yes. Okay, this is the one we need. And we're going to have a few problems in here that you would want to do. Okay, so I'm going to download it so we can actually use it. This thing opens in Word. I don't know why. Okay. All right. So stoichiometry basically is a way of figuring out how much product or how much of something you need to make something of something else, basically, right? So much of something else. Okay, so if you have a balanced equation, that's a starting point, because this right here tells me that 4 moles of ammonia combined with 5 moles of oxygen gas yield 6 moles of water plus 4 moles of nitrogen monoxide. You see? And all of these are conversion factors. Every one of them, any combination. So all stoichiometry, like I said, is refers to relative quantities of moles. So it's all about that ratio, right? Nothing but ratio. Recall that molar mass provide the factors. But molar mass is not the same for ammonia as it is for oxygen. So you cannot say that they are equivalent. They're not. The moles are, okay, but not the mass. The mass is its own. So you cannot say that 4 grams of ammonia over 5 grams of oxygen is a conversion factor. No, you need to change that to moles before you can say that's a conversion factor. Okay. So stoichiometry requires precision. So for that, you need to not use the simple amounts. Okay, so you want to use the real, like for nitrogen, you don't want to say 14 grams of nitrogen, you're going to say 14.01, you know, that kind of thing. Okay, so how many moles of water are produced if that many moles of O2 are used? Okay, so we start with what we know, which is 0.76 moles of O2. Then we convert that to whatever they're asking us, which is water, but we need that ratio first. So for every 6 waters, you have 5 moles, right? 6 moles of waters, you have 5 moles of oxygen. Now you can multiply and divide, and you've got the right answer. And there it is. And you have to watch the sig figs here too. You start with 3, you end it with 3, okay? Same thing with how many moles of NO are produced in the reaction if 17 moles are also produced. Okay, so you want 17 is what we know. And then we need that ratio between water and NO, right? And water goes on the bottom because that's what we have first. So water is 6 and NO is 4. There you go. So multiply, divide, and you get 11.33, but you have to cut it down to 11 because you only have 2 sig figs. All right, It is pretty straightforward as long, and very clearly, as long as you have a correctly balanced equation. Otherwise, you will not get the right answer because the mole ratio would not be true. All right, let's do these. Okay, so you have grams now. Remember how we did those mole conversions to grams? Yeah, we do need the molar mass. So molar mass of water is 18.202. Sorry. Okay, but here they're actually just, no, they're actually asking how many grams, but it's coming from moles. So you don't have to change the moles of ammonia, you just have to change it to moles of water and then change it to grams of water, right? By doing this ratio first. And then you've got your molar mass of water and you can determine the actual number right here, which is 51 because we only had 2 sig figs. Right. Same thing with grams of oxygen. Okay. So it says how many grams of oxygen are required to produce 0.3 moles of water? Well, in this case, we want to do 0.3 first and then do our mole ratio between water and oxygen, which is 5 and 6, right? And then multiply that times the molar mass of O2, which is 32. Right? And as long as your moles can go away, you know you placed it correctly. And you multiply and you get 8. All right, multiply, divide, because you multiply 5 times 32 divided by, times 0.3 divided by 6. All right, so let's do this one. Okay. How many grams of NO are going to be produced if you have 12 grams of oxygen and excess ammonia? That means there are no limiting reagents that are unknown. Obviously, the limiting reagent is going to be the NO. Okay. So here we go. Oh, sorry, the O2, I meant to say, not the NO. The limiting reagent is always in the reactant side. All right, so here we go. Our first thing to do is, since we're starting with 12 grams of O2, we put that down. Then we would need the molar mass of O2, right? Then we would need the mole ratio between NO and O2. And yes, the O2 is on the bottom because this O2 is on the top over here. So they need to be able to cancel. All right. And then the last thing is to do the molar mass of NO, which is 14.01 plus 16. And that'll give you 30.01. And as long as the NO can cancel, which it does, the moles, right? And you end up with grams of NO, you've got the right answer. So 12 times 4 times 30.01 divided by 32 times 5. And once you finish, you get this number, 9.0. And you do need 2 sig figs. Okay. All right, I want you guys to try just looking at this pattern, okay? And we don't always start with grams of X. We could start with moles of X, like we did in one of those problems. And we don't always go to grams of Y either. We can stop at moles of Y depending on what they're asking us. But the patterns here, and wherever you need to begin, you can. And whenever you need to end, you can also. So it doesn't have to go all the way across. All right, now, if you look at the question, look at this one. It says, for that reaction, what is the path you would take if you had this question? Okay, you notice it says, given 2 moles of H2O, calculate the grams of H2. So where would you start on the path over here? This path, right here, this thing. Oops, sorry. Sorry, this path right here. I was trying to highlight it, but I can't. I guess I have to use my annotation tool. Yeah, this one right here, this thing, right? Where would you start on there to solve this problem right here? Notice it says 2 moles of water, calculate the grams of water, and where would you end? You can type it in if you want. Or you can write it down and just wait for me to answer, but I would like to see what your answer is also. So I would really appreciate it if you text, you know, put in a message for me. There we go. Thank you. Okay. All right. You're saying moles of Y to grams of Y, but okay. You notice how you got 2 moles of water and grams of water. That is correct. You can start either gram, you know, yeah, either way. Moles of Y, grams of Y, or moles of X to grams of X, either one. That is correct. We don't know what X or Y are, right? So we're good. Yes. All right. So now you have another question to answer. All right. For this question, where would you start on this path? For these, sorry, I meant to only do one at a time. Okay. Moles of O2 required for 36 grams of H2. Where would you start? Where would you end? On that thing that I underlined, that diagram, pattern, whatever you want to call it. This one's a little different from the other one. Which one is it? Yeah, moles to grams again, but not moles of X to grams of, moles of Y to grams of Y anymore, right? This time it's moles of X to grams of Y, correct? Because you notice the grams and the moles are different. The things that we're doing, O2 and H2, they're different. They're not H2O both times, you see? So that's why you're doing moles of X to grams of Y. Okay, so next one, grams of H2 produced from grams of O2. Where do we start? Where do we end? Yep, grams of X all the way down to grams of Y. So this one uses all of them. And look at the colors that are going to come up. See? That one gives you that path. This one right here gives you this path, right? Or you can go the other way. You can start with moles of X and go to grams of Y. It doesn't matter. This one gives you this path. That's the whole thing. There you go. All right, so as you go, and let me clear all that. Okay, we have more to do. Okay, so this is helpful right here. That pattern now has those arrows. Those arrows are your conversions. That one you need the molar mass of X. For this one, you need the molar ratio from the balanced equation. And for this one, you need the molar mass of Y. Okay? So identifying where you're coming from and where you're going is very important so you can know what you need. All right. You might want to write this one down, take a picture, whatever you want to do. I would have this pattern with these little bridging data, that you'll need written down somewhere. Okay, so let's do this. An example. Okay, so you've got your balanced equation, and here's three questions that you need to answer. Try and see what you get. First one's super easy. The rest are not so easy because you got to do molar mass. So it takes a little, not that it's hard, but it just takes longer because you got to do molar mass of some of them. Okay, there you go. Let me know when you're done so I can check with you. Okay. Okay. Okay, that's looking good. Okay. One of them, I'm not getting the same answer as you, but we'll see why here in a minute. Okay. Okay. All right. So that looks good, except your I don't know why your decimals are in the wrong place, but that's weird. Oh no, never mind. They're not. Never mind. I see what's going on. The top one is not quite right because it's 0.75, right? And if you just cut it to 1/60, that would be 0.8 supposedly. So we'll see. All right. So here's the answers to these. All right. For the first one, if you did this, pat yourself on the back, and there you got it. Number two, you did that, and you got this answer, which is 26, right? Because you increase it. So it's 0.8, 26. And the last one, if you got this, pat yourself on the back because you did it right. All right. So it looks like you guys know what you're doing, or at least one of you that answered me knows what they're doing, and the other ones aren't saying anything or commenting anything. So I'm guessing they're fine. We did this already, Christina, a little bit over in the classroom. So that might be why we're not seeing more. Okay. So now we're going to keep going. And I don't think we need more of this, but there's some more if you want to practice. There's a bunch more. See? And this PowerPoint is in Canvas. So all you got to do is, do the problems, but there are no answers on these. If you notice, there are none. See, no answers, just questions. Okay, so anyway, so now let me go back to in here. I don't know why it always does that. It always tries to download it using Word. I've never associated it. I think it's just confused, and it always gives me gibberish. All right, so when we are looking at stoichiometry, we also have a concept known as the limiting reagent. So we're going to click on this, and this one is going to show you what that means. And this is another PowerPoint that I'm going to download. Hopefully it'll associate it with something, right? Yeah, they did. Okay, good. All right. not this gibberish. I don't know why it does that, but it does every time. But there's the PowerPoint. All right, so for this one, let's say you were trying to make a peanut butter and jelly sandwich, or a bunch of peanut butter and jelly sandwiches, and this is all you had, right? These are your ingredients. Oh, you don't see that? You don't see the stoichiometry module? Okay, hold on. Let me go back and see if it's closed. I don't know. That's weird. All right, let me go back to modules. I don't think it's closed off. It's right there. Oh, you're right. It is closed off. Oops. I did not notice that. Sorry about that. Okay, so thank you for letting me know. So now you can see it, right? And you should be able to see, this is the PowerPoint that I used. There's the mole conversions that we use to practice. Here's the stoichiometry. There's the limit and reagent. So this is the PowerPoint we're using right now. And this is this right here. Okay, so like I was saying, we have this stuff available. How many sandwiches can you make? That's right, 2. So you have enough to make more of the peanut butter and of the jelly, right? But you ran out of bread. So that bread limited the amount of sandwiches that you can make. Since that's the limiting reagent, right? Because that's the one ingredient that you ran out of. That's all that is. That's what this concept's about. In case of, and these are your X's, because you have more of them than you needed based on what you had available of the other stuff. Okay. So the limiting reactant is always used up in a reaction. It determines how much product you're going to make. The excess reactant is always the one that is there to make sure that the reactant is completely used. Okay. So it makes sense that the limiting reactant would be the expensive one and the excess reactant would be the cheap one, right? If you could. I mean, not always is that possible, but if you can control that, then that's what you would want, right? Plus, it's also easier to recycle, so that would make it much easier to use. All right. Now, these are your steps for doing the limiting reactant. You write a balanced equation. For each reactant, you calculate the amount of product formed. Now, in my case, instead of me calculating grams all the way, it doesn't matter what they ask me. I always do the moles because the moles is what determines really the amount, okay? So you don't have to keep going unless they ask you for both of them. If they ask you for both of them, you might as well just finish the problem. But if they only ask you to do the limiting reactant, then you first have to determine which one of those is by using the moles, and then you can keep going, okay? So you'll see what I'm talking about. And the smaller answer always indicates the limiting reactant and how much product you're gonna make. So there it goes. Here's an example. All right, something I didn't show you yet, and I need to show you. Well, I think I showed you last time, but this right here is a very good, I think it's this one. It's a very good diagram that you need to remember, because this diagram will serve you for all your conversions. Let me download it so you can see it in its entirety. Okay, It is actually part of a PowerPoint, but I like it so much that I pull it out. I pulled it out and use it as its own standalone aid for you guys. So if you look at it, let me make it a little bit smaller so you can see the whole thing. Okay, it's just kind of showing you what is needed to go from moles to mass, from moles to number of particles, from moles to liters of gas, and from moles to liters of solution. And over here, we are about to use this molar volume and the molarity. So we're going to use both of these to figure out the moles with that one problem. So let's go there. Remember this, we can always bring it back up. Excuse me. Huh. My ears are getting stopped up because it's cold in my room. Okay, so let's keep going. Okay, we were done with this. Oh man, I should have started the other one. Okay, so we were looking at this. All right, so what we want to know is which one of these is the limiting reactant and which one's the excess. You notice they're giving it to you in liters, which means we need to figure out the volume, and it's giving it to you in molar, which means we need to figure out the concentration. So molarity, and that's on this little diagram that we were looking at. See, molarity is moles per liter, and the molar volume of any gas at standard temperature and pressure, and we're assuming is 22.4 liters per mole. You see that? Okay. All right, so here we go. We are going to figure out, this is what we know, right? This is all that they gave us. And we need to figure out which one of these is our limiting reagent. To do that, you need to do your stoichiometry. Just like we said, we've been doing this. All right, so we're doing, so far we're just converting the grams of zinc to moles because we can't use anything else but moles in these kind of calculations. So the mole, we use the mole ratio from the equation. Then we have just converted to moles of hydrogen. Once we do that, now we need to convert to liters of hydrogen, right? And that gives us how many liters. All right. Now, problem with this is that liters of hydrogen and moles of hydrogen are not going to probably be what the other ones are in. So what I would do is I would just stop at this. Don't add this one, right? Just stop at the moles and see what you get. And then you've got this one that's got the liters of hydrochloric acid. And remember, 2.5 moles of molar means that you have this many moles in this many liters, right? So 2.5 moles in 1 liter. But we don't have 1 liter, we have 0.9 liters, right? So we're going to have less of it. And now we're going to figure out how many liters of that we're going to produce. Well, we could also stop at the moles. But there you go. Now comparing, that first one gave us how many? Let's see again, 27.1. Okay, so 27.1 liters are going to be made of the hydrogen gas, right? And you're going to make only 25 with this other one. Okay, so obviously your reactant that is the limiting is the hydrochloric acid, correct? Because the other one gave you more. All right, so this is where we say the limiting reactant is hydrochloric acid or HCl. The excess is the zinc. the product that we form is 25 liters of hydrogen. Why do we not choose this one? Well, remember, we couldn't keep making any more sandwiches, right? So the product was the sandwich, and the answer was 2 over here if we had had that, but we would have made more if we would just based it on the peanut butter. And we had excess bread, right? We could have made a ton more. All right. So that's the same concept right here. You have the zinc, which you have a lot of, and you have the hydrochloric acid, which you don't have enough of to finish the full reaction. So this one is how much you're going to make, period. You can't make more than that. All right. So you are going to have leftover zinc that is not going to be reacted. All right. Now here's another concept. You have the percent yield, which is, I don't know if you guys ever watched Breaking Bad. That was a TV show. And the guy always claimed that his percent yield was 99.99999, which is ridiculous, especially in organic chemistry. He was always making crystal meth. I don't know if you remember this, but if you ever watched it, it was an excellent show. Anyway, this is how you calculated it. This is how he calculated it. Apparently, he calculated the theoretical yield that he would make as being exactly almost the same as the actual yield, which is not how it usually is. So how do we do this? Okay, you're either going to be given what you made, right? Actually, you are going to always have to be given what you made, because the product of your reaction is the actual yield. But you can always calculate what you should have made, right? If the reaction had gone to completion, if you hadn't had any glitches or whatever, you would have made this much from this amount of product. I mean, from this amount of reactant. Okay, so this is how we do it. And then you multiply it times 100. Okay, so here's an example. You notice it's telling you 45.8 grams of potassium carbonate react with excess. You notice that they're already telling us that we have more than enough hydrochloric acid. So this is not the limiting reagent, and this is not a limiting reagent problem. Okay, because they're just asking us, they're telling us how much they reacted, how much they got, and they want us to calculate the theoretical amount that we would form and the percent yield. So this is a straightforward stoichiometry problem. All right, so first thing to do is to identify the two things that they're asking. Okay, so you know that you have 45.8 grams of potassium carbonate, right? And that you made from that, actually made 46.3 grams of potassium chloride. All right, so they're asking you, what should you have made if you hadn't had a problem? All right, so what you do is you take that 45.8 that they used and calculate it using your equation. Okay, that's your question. That's how much you have, right? So when you do that, you are going to need the molar mass of potassium carbonate, and you know how to calculate it. So we're not going to actually calculate it. All right, so here we go. So your actual yield is 46.3. What is your theoretical yield? Okay, let's start. We need to first convert grams to moles, right? So we need the molar mass of potassium carbonate. Remember, it's 2 potassiums, 1 carbon, and 3 oxygens. We add it all up and we get 138.21. So that is 1 mole. Now we need the mole ratio from the balanced equation. And we are looking at 1 mole of KCO3 on the bottom and 2 moles of KCl on the top. And the last thing to do is to figure out the molar mass of potassium chloride, which is just 1 potassium, 1 chlorine. Add them together and you get 74.55. Now, remember, you have to cancel every single unit up until the one that you want, which you wanted KCl, right? Grams of KCl, which is what we have. All right, so you need to multiply 45.8 times 2 times 74.55, and then divide all of it by 138.21. And your answer will be 49.4. So we need just 3 sig figs, right? Because that's how many we have here, and that's how many we have here, but this one doesn't matter, but this one does. All right, so this is the one that dictates this one. Not this, not this, none of those, this one. So we ended up with 3 sig figs, and our percent yield is going to be the actual over the theoretical. So it's 46.3 over 49.4 times 100. And this is a very good yield, by the way, because it's 93.7. That's pretty good. It's more normal than Mr. What was his name? Mr. White. Yeah, I think it was Mr. White. With all this crazy 99.9999. Okay, so that's how you do theoretical yield, theoretical amount, and percent yield. Sorry, not theoretical yield. All right. This is very useful in chemistry because after a company has been doing a certain process for many years, they have an amount. They actually calculate their percent yield every time, right? And their goal is to make as much product as they can, so they optimize the reaction so that their percent yield is as high as possible. Okay, and once they do that, then they can calculate exactly how much they're going to make, because they already know how much is going to be short when they put in a certain amount, right? Does that make sense? Okay, so let's look at how to calculate a limiting reagent. Again, no, I did not do any changes that I know of, other than made it bigger. All right, so let's go back to that module. And we have a limiting and excess reagent thing here, which we need this right here, sorry. The limiting reagent we already did, but the excess reagent we haven't. How do you calculate it? Well, unfortunately, I don't have a PowerPoint on it, but I do have a sheet that's going to help you figure it out. We're going to do all of it again. Well, in order to do one limiting, you also have to do excess, obviously, right? Because you got to figure out which one's which. So we're going to do this sheet right here, and we're going to calculate it just like it says. All right, so notice it says calculate the mass of magnesium oxide possible if 24 grams magnesium reacts with 10 grams of oxygen. All right, so I would, once again, I'm going to just go ahead. The steps, here are your steps. Step 1, balance your equation. Step 2 and 3, convert mass to moles and do the stoichiometry. And then blah, 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 it's right there. And then step 4, if whichever one is smaller, that's your limiting, and the other one's your excess. Okay. And now, to figure out how much is in excess, you need to find the amount of the remaining excess reagent. Okay, so we're going to do this whole process. I know it's hard to see it here because I couldn't I couldn't really write it correctly. So we're going to do the whole process again. Just going to bring this equation over here, which this whole question, I mean, down here where I can actually write stuff. Okay, so let's bring it down here. And we have the answer up there already, but I want you to see how this is done. Okay, so the very first thing is to figure out what they want us to do. Well, they want to figure out how much magnesium oxide they're going to make with either one of these two. One is 2.40. Okay, so remember, we're going to insert that little stoichiometry thing, which is, I think 4 is good enough on this one. Maybe it'd be more, but who knows. Okay, so we have 2.40 grams of Mg, right? For every 1 mole. Remember, this is how we do it. Of Mg, we have 24.31. Come on, click. There we go. 24.31. Oh, sorry, this thing sometimes it doesn't respond to my touch sometimes because I'm light. I have a light touch apparently. Grams, okay, of Mg. All right. Now from the balanced equation, which we haven't balanced, right? So we need to put a 2 in front of this one, right? And a 2 in front of that one, and we're balanced. Now we're balanced. Now we can say for every 2 moles of magnesium, we're going to produce 2 moles of MgO. See, light touch, MgO. Okay. Now, we want to stop here because all we want to know is how many moles we're going to produce, okay? Because that's the best way to figure out who's who. And we can come back and do the rest of it afterwards. And I'm going to show you how that works. Because this is, I believe in working smarter, not harder. And if we're done with this one, then that, oops, no, undo. I don't want you there. I want you over here. There we go. All right, so we're going to put in the same kind of thing, and we're going to make it for the next one. We have 10 grams of oxygens, right? Of O2, right? So O2. Okay, let's do this 2 to the bottom so that we are good. All right, 1. I'm just going to copy the O2 part. Okay, so we know that for every mole of O2, we have 32 grams, right, of O2. And no, the sig figs don't matter here. The only ones matter is right here. And then you notice we haven't answered it yet, but that's okay. We're going to answer them together. All right, the next one is figuring out the mole ratio, right? So according to this, we're going to produce 2 moles of magnesium oxide, right? But from 1 mole, right? Just 1 of O2. Okay. Now, let's do the math. Okay, for the first one, we're going to do 2.40 times 2. Well, actually, we don't even need to multiply times 2 because we're also dividing times 2. So we're just dividing over 24.31. And that gives us 0. Let's see, 2.4. Yeah, 2 and 2. That's just going to cancel. Okay, 2.4 times 24.30 divided. Yeah, okay, I get 0.0987. All right, so I'm going to put that number right here, 0.0987. That is moles of magnesium, right? I think that's what I got. Yeah, because it says 2.40. And then for this one, we're going to get 10 times 2, so that's 20 per node divided by 32. And that's going to give 0.625, right? Obviously, our limiting reagent is this one, right? We're going to highlight it. That's limiting. And our excess reagent, and let's just say moles of O2, right? We're going to highlight it in a different color, and that's our excess, so let's make it green. Okay, all right. So in order to figure out how much product we're going to have, we'll just keep going on the top one, right? Makes sense. We don't have to keep going, in other words. All right, so we need to now say 1 mole of MgO, right, is equal to how many grams? Let me see. Magnesium is 24.31. And the other one is 16, so it's 40.31 grams of MgO. You see that? All right, so now this was just tentative. So now we can just click and either multiply what we got, which was 0.098, right? 7 times 40.31. And we get the answer, which is 3.978. So you're going to actually make, oops, let me put it here, 3.978, so 98 grams of MgO. Okay, right? That's how much we're going to make. Okay, now, in order to figure out the excess, we have to do one more of these. And for that one, what we're going to need, so this is the limiting, right? This is the limiting, and this is how much product we're going to make. From this reaction, as is, right? Okay, there you go. All right, so now the next part is to take, you have two choices. You can either take the amount that you made and go back to oxygen, or you can start with the oxygen, with the magnesium, and figure out how much oxygen you're going to make. That makes sense? All right, so which one do you want to do? The one we just found out, or both? Actually, we can do both too. Let me put a table in. Okay, so the first one would be to take the 2.40 magnesium, right? Grams of magnesium, and figure out 1 mole. See, everything is the same except for here. We're going to have to change it. So we have our balanced equation is 2 moles of magnesium. Well, we still got to change that first. We still got to use that first 24.31, right? To bring it to moles. Okay, now we need the mole ratio. And the mole ratio says that 1 mole, right? 1 mole of O2 is going to give us 2 moles of Mg, right? Or the opposite, whatever. And now we need to just say that 1 mole of O2 is equal to 32 grams, okay, of O2. Okay, so now this is the amount that we are going to make officially, right? We would have needed, this is the amount used. So we have 2.40 times 32 divided by 24.31 times 2. And that gives us 1.57 Is it 5.7 or 5.8? 5.8. 1.58 grams of O2 is used in the reaction, right? Okay, so we started with 10.0 grams of O2, right? Oops. Sorry. What happened here? Okay, I don't know. Oh, come on, go back. It's not doing it. Hold on. Oh no, where did you go? There we go. No, yes, this is it. But where is it though? I had it in my hand. I was using it. Oh, there it is. Okay. It disappeared on me. Okay, so Control V, right? Oops, sorry. Control V, O2, minus what we actually made. That's how much is in excess. See, so this is what we had available, right? Oh, let's just say available. And this is what was used. When you subtract those two, right, you get the answer, which is your amount of excess. Okay, and that would be 10 minus 1.58 gives us 8.42. Is in excess. See? Or you could have always opted to use the other way. And I'm going to do that one for you. That way, whenever you want to, you can do whatever you want to. It's up to you. It's you know, it's like they say, to your taste. So we're going to do the table, and I'm going to show you the second way. Okay. We produced from this reaction 30.98 grams of MgO, right? Okay, so we can start with that. Okay, once again, we need to change that to moles, to moles, but we need the molar mass, which is right here. We don't even have to calculate it again. It's 40.31. Okay, so need to put 40.31 grams of MgO. Okay, is equal to 1 mole, right? Okay, now we need the mole ratio from MgO to O, because we need 2 moles, right, of MgO are made from 1 mole of O2. Let's Control V here. Okay. Now we can do the same thing, and you're going to see we're going to end up with the same number. Should be 1.58. We'll see. Okay. So 1 mole of O2, right, is equal to 32 grams of O2. All right. So if we do multiplication division, we should get the same exact number. 3.98 times 32 divided by 40.31 times 2. And I get 1.58. You see that? So we can always count on doing it either way. 1.58 grams of O2. Oops, I want to do it like this. Used in the reaction, right? And we had, so see, either one works. And you still do this to figure out the excess right here. Okay. Okay, and that's it. That's where we're stopping today. And hopefully you guys got it. And you can try doing that problem that's on there. Let me show you where it is. And let me go back to the module. I think there's one problem. I want to say there is. Okay. Yeah. A limiting an excess reagent problem. And then there's that one too. So try both of those. There are no assignments on this one. You know, no actual tests, but I want you to try these because you already went through stoichiometry before, and we'll have other stoichiometry opportunities. Oh, sorry, that's not the one. Did I just do the wrong one? I did. I did the wrong one, sorry. I meant to do the problem, which is this one. Okay. There. Okay. So do that one and bring it back done on next class period, which is Friday. Okay. No, today is Thursday. Sorry, I get confused. Sorry, Tuesday. Tuesday. I'll see you back in person. Hopefully, all of you. And I've made a note of who's here, so I don't have to take attendance already. So who's here? So I got you. You all take care. Bye.